In the last few modules, we had been looking at the Box Jenkins models. Primarily, we had been looking at special cases of the autoregressive model of order P, the moving average model of order Q, and in general the ARMA model of order P and Q. We have also extended these models to the ARIMA model and the SARIMA model meant for non-stationary processes. We have studied the properties of this model, but what we will do today is to look at how we build up the models. So, given a data set, which model is going to be the best one, and if so, what are the orders of this model, that is what is P and Q going to be like, or the differencing factor D. So, we need to choose this and then we need to build up the model, estimate the parameters. So, primarily as we will see that there are three steps in doing this. One is the identification of the model, the other is the estimation, and finally, we will have to look at the diagnostics to see if we have a good fit for the model. Some of this we have already covered. So, we will just have a very quick look as to how we incorporate this into one big model building method. Let us look at how to build the ARMA model. The model is x t is alpha 1, x t minus 1, etc. up to alpha p, x t minus p, and then you have the innovations epsilon t plus beta 1 epsilon t minus 1 plus etc. up to beta q epsilon t minus q. So, epsilon t's as before are white noise with 0 mean and variance sigma square. The model can be written in the short form as phi b x t is equal to psi b epsilon t. The autoregressive integrated moving average model or the ARIMA model is just a variant of the ARMA model, where you add on the differencing factor 1 minus b to the power of d. So, if you have a trend, then this 1 minus b to the power of d, this differencing would reduce the stationarity of the trend into a stationary component, and then you fit a ARMA model to it. If you have a seasonality component, then you use the SARIMA model, and in this case you have both trend and seasonality which can be removed, and then the ARMA model fitted to the resultant stationary model. Now, how do you build on either the ARIMA or the SARIMA model or the ARMA model in general? There are three distinct steps involved. The first of them is the problem of identification. That is, a choice is to be made regarding the time or type of model that we are going to look at. There will be several candidate models, and we will have to identify the best model for our data. Once we have identified the model, then we have to estimate its parameters. So, for example, we select that it should be an AR model of order 3, then we will have to look at the 3 parameters of the AR model and how to estimate them. We will also need to estimate the variance parameter. So, the estimation part would come in. The third part is the diagnostics part. Here we check whether the estimated model adequately fits the data or not. So, this is basically a check for the goodness of fit of the model. Very often what happens is that when you actually estimate the parameters and fit the model, you find that the fit does not come out to be very good. In that case, what you can do is you can go back and look at another candidate model and see if that gives you a better fit or not. As we will see that there will be several candidate models when we are looking at the Box Jenkins type of models. Let us look at the problem of identification first. To decide whether differencing is required to eliminate non-stationarity, that is the first thing that we need to look at. That is, what should be the orders of small d and or that of capital D. Remember, the small d actually represents the order of the differencing for the trend. So, how many differencing is required to remove trend? That would decide what small d is like. Capital T is the differencing order for the seasonality. So, again, how many differencing we would require to remove seasonality, that needs to be decided on. If there is only trend, we need to look at only small d. If there is only seasonality, we need to look at only capital D. But very often there will be both, and hence we must check for the orders of both the d's, the small and the capital. After we have done this, we can actually reduce the model to a stationary one, and then we would need to fit a ARMA process to this. And when doing so, the first thing that you would require is to decide on what the orders of the autoregressive component P and the order of the moving average component Q must be. So, we need to look carefully as to the alternative choices of P and Q. Very often there will be several candidate models, and the final model may not be identified at the first go. So, we need to go back and forth and see which of these models will give us the best fit. Why does this happen? We will see that in a moment. Now, let us first look at the choice of small d and capital D. So, let us look at small d. Now, the differencing order can be judged either from a visual plot of the difference series or from the autocorrelations. Now, if we have a stationary process, the plot should exhibit no trend or seasonality, and it should look similar in the different parts of it. Now, visually this can be at times difficult, particularly for inexperienced people, but once you get used to it, it is not so difficult as to see whether at least you have been able to eliminate trend and seasonality. It really means that you do not have an increasing time series or a decreasing time series. That is, you will have a more or less a flat sort of plot, and in that case, if you do not have seasonality, then this flat would be more or less look like random. It would not be random basically, but it would not have a very regular pattern or oscillation. So, that would tell us that there is no trend or seasonality. But since this is difficult to do, very often what we do is we look at the autocorrelations. Now, for a non-stationary series, the autocorrelation function dies off very slowly. So, it does not go to 0 very quickly as h increases. So, if you see that there is a large lag for rho, that is for the autocorrelation function, which is non-zero, then you can expect that there is some form of non-stationarity in the data. And then what you do is you difference the series and then do the autocorrelations for the different series. See if now the autocorrelation function is going down much quicker, keep doing this until it actually does go down quicker. So, that way we can actually identify and eliminate the non-stationary part. Let us have a quick look at what these two means. First of all, the visual plot. On the left hand panel, we have a data, and you can see that if you plot this data, this is an increasing function. So, it starts somewhere around 800, a little more than 800, and ends up beyond 1200. So, this is there is a increasing trend in this data. Now, on the right hand side in the first panel, what we see is the first difference of the series, and now what you see is that the series has actually flattened out and is oscillating around the 0 line in this case. So, we can do a second differencing, which is the lower panel on the right hand side, and you can again see that this is oscillating around 0. So, we can feel that if we do 1 or 2 differencing, then probably we can get rid of the trend value here. But the problem is that how many differencing? 1 or 2? Both looks more or less similar. The point here is that you should not be differencing too many times if possible. So, in this case, 1 differencing should be sufficient, and what happens is that if you keep differencing more than required, then you might be bringing in some spurious oscillation. So, that should be avoided, and once this flattens out, you stop. So, in this case possibly d equal to 1 is good enough to get rid of the non-stationarity. But as I said, visually it may be a little difficult initially to identify how many differencing we need to do. We can see that with differencing we are getting rid of trend, but how many of these differences may not be so readily understandable. The other way of doing it too is to check the SEF. First, look at the diagram in the lower panel. In this case, we have a trend, and you can see that even at a lag of 25-26, the trend there is a very high value of the autocorrelation. I will explain what the dotted lines are as I go along, but you can see that these are above the dotted lines, and you will only assume this to be 0 if they go below the dotted line. So, in this case the values are significantly large, and since it is a lag 25 where we still do not have insignificant values, we will say that there must be some non-stationarity, and this shows that in this case it is because of a presence of trend. In the upper panel you have non-stationarity, but you can see that this is sporadic. So, after 3-4 stages you are getting non-stationarity. These are primarily because there is a seasonality in the data, and this non-stationarity again persists up to the 25th, 26th values. So, these two pictures tell us actually that if you have non-stationarity either in the mean or in the seasonality or in the trend, you can look at the SEF functions and find out whether the process is stationary or not. Once we have reduced the process to a stationary one by identifying the d values, that is a small and a capital D, and then differencing accordingly. So, once having the differences series, then what we are reduced to is a stationary process, and now what we do is we fit a ARMA PQ to this model. How do you choose? Now, you actually look at the difference series, the stationary one, and do the ACF for that. If the ACF becomes 0 beyond the time point, say the time point m, then we know that it is a moving average of order m. If the PACF becomes 0 beyond the time point m, then we would expect it to be a autoregressive of order m. But if both show several significant values, then we know that we need to fit in an ARMA PQ with some orders, preferably a low order ARMA. We need to look for a model which is parsimonious in the sense that it has low values of P and Q. We will see how we do this. Now, remember that if you have a ARMA PQ, you can write it as a AR infinity. So, and series, if you have a ARs of very high order, say 10 or 12, then probably it can be substituted by a ARMA 1-1 or ARMA 1-2 or 2-1. So, these would be alternative candidates. Similarly, if you have a MA of reasonably high order, maybe MA 8, MA 9, then possibly again a small ARMA model with orders like p equal to 1 and q equal to 2 might give you a equivalent fit or even a better fit. What happens here is that if you have too many parameters in the model, then you have to estimate too many unknowns, and that actually reduces the efficiency of the estimates. So, what we would like to do is to have a model with as few parameters as possible, and that is the reason why we would not choose AR12 and instead go for a ARMA 1-2 if that is possible. So, that is how we select between models. There will be several candidates and we will choose the one which has the smallest number of parameters, because that would give us efficient estimates, and if you have efficient estimates, the forecasting would be better in the sense of less prediction errors in the forecast. Now, there is one problem that we have not addressed here, and that is the problem of the ACF. We have assumed that rho h goes to 0 or becomes 0, but rho h is something that is unknown. Instead, what we look at is the RH, which we calculate from the samples. Now, RH is equal to gamma hat h by gamma hat naught, as you remember, and unfortunately, these are seldom going to be 0, even if the rho h's are. So, RHs need to be checked for significance. So, if they are insignificant, you will say that the corresponding rho h can be taken to be 0. Now, the RHs are normally distributed asymptotically with mean 0 and variance 1 by n. Hence, for significance of RHs, we would look at the interval minus 1.96 n to the power minus half and 1.96 n to the power minus half. If the RH value is within this interval, we will say that it is insignificant and we will stop going beyond that value. But if the RH values are outside the interval, there is some significant rho h still that we need to take care of. Now, if you remember in the correlograms that I showed you, there were two dotted lines, one above the 0 line, one below the 0 lines. These are primarily the minus 1.96 n to the power minus half line and the plus 1.96 n to the power minus half line. So, if the plots actually the spikes go below this dotted lines, you know that the values have become insignificant. So, if RH is insignificant, it goes below the lines. If it is significant, it should be lying outside this interval. Once having selected the model, selected in the D, the capital D, the P and the Q, we look at the method of estimation. Now, the methods of estimation we have discussed, and we are not going to go into details. Very briefly, for the ARP, we will use the Durbin-Levinson algorithm generally. For the MAQ, we will be using the innovations algorithm, and for the ARMA PQ model, we have the innovation algorithm and the subsequent equation solving for the AR and the MA parameters. We have discussed this, so we will not go into the details, and we have also said that we can use the ML method as an alternative method. Very often what is done is that the first methods actually are taken as initial estimates, and these are then used in the ML method for the recursive or the iterations that we need to do, and then we can use the ML method to get a final solution. Finally, we look at diagnostic checking. Now, since there are always several candidate models, it is necessary to check the goodness of fit of the selected model, and then if necessary go back and look for a better alternative. The two things that we need to look at are the randomness of the residuals and the model selection criteria. Firstly, the residuals. Now, the residuals are defined as ET, which is the observed value x t minus the predicted value x t hat. Now, E t should be white noise, because these are standing in place of the errors. So, what we do is we compute the SCF of the E t's. So, let us call this R E h, the autocorrelation functions of the residuals. And if you plot this R E h against h, remember this should be a purely random process, and hence should have a single spike at 0 and should be insignificant everywhere. If that happens, we know that we have fitted the model well enough, and whatever is left is random and we cannot do much about it. But again, this is difficult to do visually. Sometimes even if you have got randomness, there would be a sporadic spike somewhere which goes beyond the limits, etc. So, can we get a formal test for this? Now, there are several tests. The simplest of them is the portmanteau test. What it does is, it says that the RHs are going to be 0 for large H, because as we just said, if you have randomness, then it should be just R 0 equal to 1 and everything else should be going to 0. So, they do not stop at the first step, they take say m steps. So, H equal to m up to m, and then they square up the residuals and sum them up, and n times that can be shown to be chi square m. Similarly, a refinement of this is the June box test. It is a similar test, but there are some other factors like n into n plus 1, n into n plus 2 and n minus h which comes in. And then again they showed that this is chi square m, and in either case you reject the randomness of errors if the chi square value observed is larger than the cutoff point of chi square m alpha. So, you can do this test. If there is randomness, these values are going to be small. If there is non-randomness, these values are going to be large. The other two tests would be, one of them is the turning point test. You look at the difference between x t and x t minus 1, which we will call d t. A turning point at t is 1 which has d t greater than 0 and d t plus 1 less than 0. So, x t is larger than both x t minus 1 and x t plus 1, or it could be the other way around, x t is smaller than both. So, the d t is less than 0 and d t plus 1 is greater than 0. And we see that how many turning points are there. So, let z be the number of turning points, and it can be shown that z follows a normal distribution with mean twice n minus 2 by 3 and variance 16n minus 29 by 90. And we reject randomness if the modulus of z minus mu z by sigma z exceeds the tau value of 1.96. Usually z too large means there is too many changes, too many turning points, which means there is a negative correlation. Z too small means that there are too few turning points and there is a positive correlation. In either case, the values are not going to be random. So, it should be somewhere in between, and if it is negatively or positively large z minus mu z, then we should be rejecting the hypothesis of randomness. Another test is the sign test, where let w be the number of dt's which are positive, and we can show that. So, this is the sign of the difference, and we can show that w is again normal with mean n minus 1 by 2 and variance n plus 1 by 12. And again, if w minus mu w by sigma w is large, absolutely greater than 1.96, we will say that we do not have randomness. Positively too large means increasing trend, negatively too large means decreasing trend. Finally, the model selection criteria. Now, let theta hat be the estimates of the parameters, alpha hat, beta hat. We get this by the maximum likelihood method, and let sigma hat square be the sum of the residuals divided by n. Then we have what is referred to as the final prediction error criteria, which is the FPE, which is sigma hat square into n plus p plus q by n minus p plus q. Now, notice that if you have p plus q large, then sigma hat square is going to be small, because you have a large model and the errors, most of the model would be accounted for, and the errors would be small and the error variance would be small also. So, the first term would be small, but if you look at n plus p plus q by n minus p plus q, as p plus q increases, this increases. So, there is a trade off. Sigma hat square is going to be smaller and smaller the larger p plus q is, and the second term is going to be larger and larger as p plus q increases. So, we need to choose a model which minimizes the final prediction error. So, there would be a trade off and there would be a single minimum where we can actually look at. An alternative to it, or a more refined version, is the Akaike's information criteria. Again, this is composed of two parts. The first part is based on the likelihood, and you are maximizing the likelihood. Therefore, minus 2 log of that would be minimized as you get a better fit. But the second term again depends on p plus q, and it would be increasing. So, first term would be decreasing with p plus q, the second term would be increasing, and you would like the whole of the AIC, you get this whole of the AIC, and you would want it to be as small as possible. So, there again would be a trade off, and you can choose the best p plus q, which would minimize the AIC. A criteria which accounts for some bias that the AIC have, we will not go into the mathematics of it, is the AICC. This is a bias corrected AIC, and you can see it is similar to the AIC, except that the second term is somewhat different. It involves n, and this can also be used as a model selection criteria. So, what you need to do is you need to look at the randomness of the errors and then look at the model selection criteria. Choose the model among the alternative models or all the candidate models that gives you the minimum AIC or the minimum AICC, and that also has random errors. In today's lecture, we have seen how to build a Box Jenkins model. So, there are several choices that we can have for a given data set, several alternative models that we can use, and we have seen how to choose among them. Primarily, there are three things that we need to look at. The first is the problem of identification, the second is the estimation problem, and the third is the diagnostics. Now, you do not select a model at one go. So, what happens is that since there are several candidate models, you need to go backward and forward in choosing the models. So, you choose a model, look at the different steps, estimate its parameters, look at their diagnostics, and see if the fit is not good enough, you select another alternative candidate. And this way we can finally choose a model. Primarily, to do that, we would require the model selection criteria, which we have already described. We will also need to look at the randomness of the errors, because once we have random errors, we know that there is nothing else that we need to look after when building the model.